Hello guys, it's me, Miss Williams, as you should know by now, and if not, we have bigger problems. But hopefully you watched the video before this where I talked about the plate tectonic project. Again, that is for your test grade. It is an easy 100 as long as you just do what the packet tells you, easy 100. Anyways, if you have no idea what I just talked about, go back and watch that video, and then come back and do this. So, in this lecture, we're going to be talking about plate tectonics. So, again, if I'm looking down to the notes, just so I can help y'all follow along in the PowerPoint. Let's see. So, plate tectonics. I've mentioned this several times. This is the stuff that caused Pangea to break up. This is the stuff that causes mountains. This is the stuff that causes mid-ocean trenches. Plate tectonics is kind of like what I discussed, floating on this magma-like substance and all of that fun jive. So this is basically the breakdown of how what we see on the top of our planet, the crust, moves and shapes everything. So there are 4 main layers to our Earth. Just like we talked about the different layers of the sun, our planet also has different layers. So in your notes right there, it says the Earth is divided into 4 main layers, and it's based on composition and state of matter. So as we can see here in the picture, we have the inner core, the outer core, the mantle, and the crust. Now there is a small section in here called the asthenosphere. We'll talk about that a little bit, but these are your 4 main layers. So the inner core. The inner core is solid. That's your first blank right there at A. It is very hot, but it is solid because it's under so much pressure. So we kind of talked about the relationship between pressure and temperature for some of the ocean stuff. But in this case, it's going to be a hotter temperature, not a cold temperature like the depth of the ocean. So the inner core is solid. It's very hot, but it's only a solid because of the pressure, not just the temperature. And we believe it is made of solid iron because iron is one of the most dense elements inside of our Earth. So all of that pressure would push it down to the center, and it would be a solid iron core. So those are your 2 blanks for A right there. Inner core solid, and then made of solid iron. So next is the outer core. So here we have the inner core. That's the solid iron. Next we're going to talk about the outer core. It's a little different, but so this one is liquid. I know it doesn't really make much sense, right? Solid, then straight to liquid. But yeah, so the outer core is liquid. It's made of both iron and nickel. So it's a mixture here. So we have inner core, just iron, and it's solid. Outer core is going to be liquid iron and nickel. So the first blank right there for B is liquid, and it's made of iron and nickel. And you can tell it's a little bit thicker than the inner core. The next part is the mantle. This is the thickest section of the inside of our Earth. So it's a liquid, but it's kind of like a thick liquid. So it's like a peanut butter-like consistency. It can flow and move, but it's almost a solid in certain places. So pressure does play a big deal in this, but so does temperature. So some of the cooler spots are going to be more solid, and then the warmer spots are going to be more liquidy. And this makes sense because this is a layer that convection currents take place in. Hold on. Just checking. Okay, yeah, so this is a layer that convection currents take place in. And again, we have talked about convection currents all semester long. Like, if you don't know what convection heat transfer is by now, I have failed you as a teacher. But mantle, thickest section, it's mostly liquid substance, but it can be more solid in places. And it's made of more lighter elements than the inner and outer core. And again, it has convection currents. So we have the heat radiating off of the core, and that's going to make this material rise because it's hot. And as it's rising, it's going to cool down. Once it cools down, it falls. And this process makes a current, which is what we call the convection currents. And also, these convection currents are what cause like magma plumes and stuff like that to come up and kind of, do volcanoes and things like that. So, let's see. those blanks for that last one. So for C, it's going to be liquid, and then made of lighter elements, and then convection currents occur in the mantle. Those are going to be the blanks right there for C. So for D, the crust. This is the part that we live on. So the crust is solid and rocky. So that's going to be your first blank. We live on the crust. It's made of mostly oxygen and silicon. So whenever we talked about mineral groups, this would be your silicates and stuff like that. And of course, we've got a lot of oxygen and different things. We've got oxides. We've got an O in a majority of the minerals, and then of course in water. So in the crust, there's a lot of oxygen and silicon. And we already know that it's made up of rocks and sediments are just broken down rocks or organic material. And the big idea for this is that the crust is divided into plates that move around. So you can kind of picture the plates as like huge puzzle pieces. But puzzle pieces are kind of floating, so we can kind of like move them a little bit. And yeah, so that's how you kind of want to picture the crust. You don't want to like, it's not like floating on water, but it's like, I'm trying to think of a good thing. So let's say you're making a cake, and you make the cake, you don't let it cool, and you put the icing on, and then you try to put like little stuff on top of the icing. The stuff on top of the icing is going to kind of be moving, because that icing is kind of acting like a little thing that's making it float on there. And if none of y'all bake, I'm sorry for that analogy, but that's a pretty okay one. Okay, I went too much. So next part, 2, convection in the mantle. So since the mantle is a liquid, the material can flow. So convection currents cause the material to move around, kind of like I was discussing earlier. We've got the heat coming up, it's cooling down, so it's dropping back, and it's creating these currents. A convection current is whenever the material is heated and it becomes less dense and it rises. So then it cools, becomes more dense, and it sinks. Kind of like the air did in our meteorology unit. The hot air rose, cooled down, sunk, and that's how we got different fronts. So right there in those blanks. Since the mantle is slushy like a thick liquid, the material can flow, and then convection currents cause the material to move around. So convection currents is that one blank. And then B, where it says convection current, when material is heated, it becomes less dense. That's your first blank. And then whenever it cools, it becomes more dense. That's your second blank. Okay, so now on to number 3, plate tectonics. So now that we've got the layers of the earth down, we need to talk about those pieces that are floating on top that we live on. So plate tectonics, this is the solid outer part of the crust and the upper mantle. This is called the lithosphere. Sorry if my speech impediment made that a little weird, but a lithosphere. So this floats on the liquid-like part of the mantle, and this is called the asthenosphere, which is what I mentioned a couple slides back. So it's like we have the mantle, and then we have the crust, and the crust is kind of broken down. We have that boundary between the mantle and the crust. So like this is the asthenosphere, mantle. So we have that in-between section, and then we have the lithosphere, which is the top hard part of the crust. So the lithosphere is broken into sections called plates. So the plates get carried along as the asthenosphere moves with the convection currents, like a raft in the river almost. So in the blanks right there in your notes, the solid outer part of the crust and upper mantle is called the lithosphere. And then the lithosphere floats on the liquid-like part of the mantle, which is called the asthenosphere. So those are the blanks right there in your notes. Let's see. And then there's one more on the next page. The lithosphere is broken into sections called plates. And that's where we get tectonic plates from, is these broken pieces of the lithosphere, and then those move and do all the fun stuff that we like to look at. All right, so here's just a couple pictures. Again, here's another convection cell with convection currents. The asthenosphere is the layer right underneath the hard part, and then the lithosphere is the hard part. And then here is a map of the different tectonic plates. So we are on the North American plate. That includes part of Central America, North America, and the stuff up to the pole right here. there's 2 small plates here, there's another small plate here, but all of these are the big, what we call puzzle pieces almost, that's floating on top of that asthenosphere. So these are kind of like the puzzle pieces that move. So right here is where the Himalayan mountains are occurring because all of these plates are moving together. The Pacific plate is moving underneath our North American plate right here. That's what causes a subduction zone. And we've got a lot of different stuff around here. But this Pacific plate that goes from here and then to the other picture here, that's where your ring of fire is going to be. But we'll talk more about that later in a different video. So this man's pretty important whenever we talk about plate tectonics because his theory kind of explains why these pieces or these puzzle pieces of our continents look like we could just kind of put them right together. So Alfred Wagner believed that the crust of the earth moved as early as the 1800s, but he couldn't explain what made them move because, early scientists, they didn't have all the tools, they didn't have all the knowledge yet, but they're like, something's happening, can't explain it, but it's happening. So he called his idea continental drift, and there are 4 reasons that he thought the plates were moving. Clearly not because we could look out this window here and see them moving, but there was a lot of other large-scale reasons that he thought this was true. So 1, the most obvious. The shapes of the continents look like they can fit together like a puzzle. So this is what a lot of kids notice whenever they first start looking at maps and start to realize what's happening. They're like, oh, if we just kind of move them here, here, and here, they look like they go together. So this brought up the idea of the supercontinent called Pangaea. Now this is one of the pages in your project, so either pay attention here or you can look it up later. But Pangaea was the first supercontinent that we think occurred whenever all the continents were together. So later on it breaks down into smaller supercontinents and stuff like that, but the first one that we mostly talk about is Pangaea. So that's his number 1 reasoning, because they all look like they fit together. So he believes that they all once were together. So number 2, fossils. So we kind of talked about this. We refer to these as index fossils. So they would find the same fossils over in Europe as they did in North America or South America. So these fossils are on continents that if we moved the continents together, they look like they would be in the same areas, as you can see in this picture here. Like these were here, and these were here. So whenever they're all pushed together, that makes sense. They're all in the same area. That's why all the fossils are there. But once we take these continents back apart, we're like, how did we get the same animal as this person? Why is this rock with this animal in it just like it is over there in a different continent? So they assume that these continents lined up these rocks and these fossil evidence together whenever they were part of Pangaea. So that's number 2 of why Alfred thought all of this stuff was once together and they moved apart. Number 3, I kind of actually talked about this with number 2, but rock types and mountain ranges. So he saw and he noticed that different mountain ranges matched up their rock types and different features on different continents. So our Appalachian Mountains is actually part of another mountain range in a different country. Sorry, people keep trying to contact me. But so that's why he thought these were once together, because these mountain ranges and rock types line up. And number 4, warm climate fossils are found in Antarctica. So we should not be finding fossils of animals that lived in warm climates at one of our poles. So the only thing that made sense to him and other scientists was, at one point, this rock, before it was a rock, so this ground, was in a warmer environment to allow these animals to live. So, and then after those animals were died and preserved in the rocks, then the continent shifted to a colder climate. So, if we're finding warm climate fossils in Antarctica, that has to be evidence that there used to be a tropical environment there where there's now glaciers. There's really not another explanation for that. So that's his fourth reasoning as to why he thought the continents moved. Yeah, so all of those you should be able to easily find those blanks right there for your notes. And that is it for this lecture on plate tectonics. We will be talking about plate boundaries. So the picture that we saw back here, we will be talking about the different features that are occurring along these boundary lines here. So again, make sure you're working on your project and make sure you are doing makeup work if you need to. Please email me if you have any questions. Bye, guys.